In the last several lectures, we've really focused on applications in 3 dimensions. We've been talking a lot about volume. In this lecture, we're going to take a big step backwards and look at an application of integration in 1 dimension. We're going to look at developing a formula that we can use to find the length of a curve. So we're going to follow a very familiar pattern to do this. If we want to find the area from A to B, well, we're going to follow our familiar pattern. We're going to divide this into n subintervals. And the length of those intervals, delta x, will be b minus a over n. And then what we're going to do is we're going to come up with an approximation for the area, for the arc length of the curve on each of those subintervals. Add them up, limit as n goes to infinity. It's going to turn into an integral, and that's going to be our formula. Right, so let's say we're looking at an interval here, and I'm actually going to draw this to be a fairly large interval, just so you can see what I'm doing. So if we have an interval here, right, this is delta x, and what I'm going to do is I'm going to draw a right triangle in here. Right, then this distance here, the horizontal distance, is delta x. I'm going to call this distance up here delta y. Then I'm going to draw in the hypotenuse here. You'll notice that hypotenuse is really close to having the same length as the length of the corresponding arc that runs above it. So what's the length of this hypotenuse here? Well, this is the Pythagorean theorem, right? This is the square root of delta x squared plus delta y squared. So the approximate value for my arc length is going to be the sum I equals 1 to n of this square root, delta x squared plus delta y squared. Now that's nice, but I really need that delta y to be out of there, right? Because it's delta x that goes to 0 as n goes to infinity, and I don't really know what's going on with delta y. So that needs to go. All right, so here's what I'm going to do. I'm going to flash back a little, and I'm going to use the mean value theorem here. Remember what the mean value theorem says. It says if we have a continuous function, so okay, we're going to have that restriction. If we have a continuous function, then I have 2 points, like these points here, the boundary of my delta x interval there. Then there exists a point on that interval so that the derivative of the function at that point is equal to the slope of the secant line. Right, well, the slope of the secant line, that's my hypotenuse. Right, my hypotenuse is the secant line. And its slope is just delta y divided by delta x. Right, and then, like I said, the mean value theorem says that there exists a point on this interval somewhere, let's call it x sub c, such that f prime of x sub c is equal to that slope. All right, and that's the formula that I need to get rid of delta y. Right, if I multiply both sides of this by delta x, delta y is equal to f prime of x sub c delta x, and now let's make that substitution. Right, now my arc length is approximately the sum I equals 1 to n square root delta x squared plus delta x squared f prime x sub c squared, and now I'll put the square root in there. Excellent. My delta y is gone. All I've got in there are delta x's. So I'm going to factor that delta x out. Excuse me, I'm going to factor the delta x squared out. And the square root of that is just delta x. So my area here, this is the sum I equals 1 to n delta x square root of 1 plus f prime of x sub c. Awesome. Now I'm going to take my limit. Right, if we take the limit of this as n goes to infinity, then I get the exact arc length. S is equal to the limit, n goes to infinity, sum I equals 1 to n delta x, square root 1 plus, oh, I lost a square. This should be the derivative squared here. So this is 1 plus f prime of x squared. And of course, this limit as n goes to infinity. That's our integral. So this is the integral from a to b of the square root of 1 plus f prime of x squared dx. And there's my formula. Right? That's the formula we're going to use to find the arc length of a function. So I've got the complete formula here, and the part that I really want to highlight is this part here that says the function we're talking about has to have a continuous first derivative. Back in the derivation, at the step where we pulled the mean value theorem in, the mean value theorem has some continuity requirements. Right? And so in order for us to use something derived from it, those requirements have to be met. So before we can use this formula, we are going to have to make sure that the function whose graph we're trying to find the length of does have this continuous first derivative. And we'll see some examples later on here where that does become an issue. Okay, so now that we've got that function in hand, in the next lecture, we're going to look at some specific examples, see how we can actually find the lengths of the graphs of some functions.